So I'm going to talk about Pcb.Py. Now, I cannot talk about this without introducing FREP, because I think it's such an elegant idea. So let me just show you what FREP is and what contributions I have to propose for it. So FREP, it's an entirely functional representation for any 3D object, really. Neil used JSON in his implementation. I think it's a good idea because it makes it more compatible with any other interpreter that you would want to use to render the shape. So the idea, the beef is here, right? You have a function of x, y, and z. And if it's true, then you are inside the object. That's it. That's the core concept. Okay. Now to produce this, you could do it in any language you want, but the proposed way is to use Python, and in particular, you have Pcb.Py, which lets you design PCBs. But you could really do anything else you want with the FREP concept. And after you have this JSON with the logical function, you can do a rasterizing. Now this step is really interesting because you can do it at any resolution you want. It could be 2D, it could be 3D, it could be something else entirely. I think you could even do meshes. But yeah, for PCBs, it's sufficient to just get an image output, because that's all you need to do to compute the routing. Now, just some examples. If you want to make a circle, then this is the function. If you want to add shapes, you simply have to do a logical OR. That's all it takes. And if you want to subtract, then you would first negate one of them and do an AND. It's really elegant. I really like this system. And notice how X, Y, and Z are just not defined yet, because this happens in the rasterizer. You define yourself the area that you want to render and that you want to get. Now, the improvement I made last year, FREP GPU, it's a faster rasterizer that is based on OpenGL, because previously this FREP was entirely CPU based. It was pretty fast because it was using NumPy, so there was still CPU vectorization, but GPUs are even better for that. Nowadays you have thousands of cores on a GPU. They are very dumb, but they, as long as the code is relatively short, they can perfectly do it in real time even. So that's why I was excited to parallelize FREP on the GPU. But for that, there were a few changes that I really needed to introduce on the syntax of the JSON file. So most importantly, now the syntax is more like C and less like Python/NumPy. It's entirely C. The typing is really important. If you mess it up, then it just won't compile in the shader. So you don't have to worry about this, of course, because I also have a new version of PCB that takes care of that. Another important change, now you have a list of functions, not just one, because I wanted a concept of color and transparency. So each function is purely binary. If you want to add a color, then that's a separate argument. And you also have alpha. And the idea is that if you want multiple colors, then you will have different functions of space with each its own color. Okay. Yeah. Finally, the really exciting thing about FREP GPU, and I think that's the main reason to adopt it, it's the real-time update. So you see this Python script that will generate the JSON. Usually you have to relaunch it every time you want to update the render. But now I also accept Python file as an input. So I will show you in a minute, but essentially the previous frep was taking the JSON as a stream. Now I take it as a file path, but I also take Python file path. It could be either. If it's a Python script, then frep GPU itself creates a process that calls the Python script, produces the JSON, and updates the view. So you don't have to do anything. You just have to modify your design file, you save it, and it updates. You will see it in a minute. And yeah, now I just wanted to compare the speed. Now, of course, there's a price to pay. You need to compile the shader, so there's a fixed compilation time that's added. But after that, it's basically instantaneous. It's 1 millisecond on a desktop PC. On this kind of PC, it's going to be probably a few milliseconds, but not more. So you can really design in real time, as long as the compilation of the shader is not too long. So that's probably still something we can improve. But obviously, now if you want to have a 1000 dpi preview of your board, previously you had to wait like 20 seconds. Now it's you don't even notice. So that's the most exciting results from that, I think. Now you do have to keep in mind that this version is not compatible with the previous frep. That means that it's a fork. Okay, let's see on the GitLab. So this is Pcb.Py from Neil, and it comes with frep. But now, if you go to this link.
Sorry, just on that, Quentin, this is all fabulous. I would encourage you, let's kill off the Fab Cloud Pcb.Py and just make it redirect over to here. I'll keep tinkering on the MIT one for experimental things, but let's kill off the old one and just move to the new one.
Yeah. Okay. So if I have your consent, then I guess this can become the new default, but I still need people to test it because it's very early.
Yep.
Now, if you go to this one, you will see there's also an frep. So if you don't run the GPU, that's perfectly fine. I also prepared a new frep that's compatible with the new JSON format. Okay, so that's entirely up to you. And if you go to examples, you will also see PCB, which is also updated slightly to be compatible with the JSON format, right?
How easy would it be to make a little parser to go from old to new?
Pretty easy. Very easy, actually. I should have thought about it.
Yeah, just because since I have so many of the old examples in the Hello Worlds, the parser to go from old to new would be a nice thing. Puneet, this does need the GPU. In the queue, I think either Quentin and I can also write a multi-core CPU version. That wouldn't be too difficult. But Quentin's version does need a GPU.
Yeah. Yeah, just to explain about the translation, if you were to do it, you see that almost everything is the same. Well, now we have limits, but you could also go with previously it was xmin, xmax. Oh, sorry, that's the chat. I will put it here so I see. Good. And yeah, the biggest change, as I said, it's the list of function. Each function has its own color in hexadecimal and transparency, but honestly, apart from that, it's all the same now. So I think it could be tricky to translate if you mixed the color with the function, which could happen sometimes in the previous implementation.
Oh, but that was a hack I didn't like.
Yeah.
So yeah, keeping an eye on time, let's get up to the demo.
Yeah. We really have to get going. So I prepared here a super basic example with shapes, but I will not spend too much time on that because it's not a PCB. but it's just to show you the new syntax. So previously you would just run the Python script, basic.yes, and you get a JSON stream, and that would become the input to frep. Yes, and then you have to specify the DPI. So let's say 500. You run that, and you get an image, and you can see that it's a super basic shape. Maybe you can see the red square is a bit transparent because it had alpha. Okay, so that's the old syntax. Now, if you want to do exactly the same with frep GPU, you don't call your script, you just call frep GPU, and you have the input argument. This could be a JSON file or a Python script. In this case, I will just give it the Python script, and that's basically it. Now I'll just specify the DPI with D, and I will say R so that it reloads automatically. And I get my render, and now it's super cool because I can change it in real time. Let's change the color maybe. So you see it's really instantaneous. But that's because it's a simple example. If you go to more complex, especially in PCBs, you have a lot of text that could be a bit slower. But let's go to PCB. So I prepared a file. It's simply a copy of pcb.py, and it comes with all these primitive functions. But most importantly, it comes with all the parts that Neil put there by hand. I think we could improve that, but for now it's all in the Python script. Because of that, the Python script is 8,000 lines of code.
But sorry, just a note on that, or actually do the demo, then I'll make the notes on that. So keep going.
But I know what you want to to say. I think the benefit is that it's a single file, right? You just take it.
Well, okay, so it's a couple. Do the demo so people. Do the demo, then I'll make a couple comments.
Right. So if you go to the bottom of this file, after all the definition of the parts, then you see the real deal. We define the board size, we define the origin, and all those units are in inches because it's defined right here. Okay, millimeters per unit is 25.4. So we know it's inches. You could change that if you want. But inches is convenient for PCBs, of course, because mils is 1,000th of an inch. And your PCB is here. It has the size you wanted. And if you just want to add the components, I'm cheating a bit here. I prepared something. It's gonna be an ATtiny. It's gonna be located relative to the origin at 0.6, 0.56. Okay, let's run it. So again, I'm gonna use my frep GPU and the inputs. Yeah, this one. Now the DPI, I don't know what would be comfortable here, but let's try with 500. I think that's okay. So a couple of things here. You see the single component that I put. The ground pin is labeled with this little notch. Now there are many different rendering options. If you want to have the labels, for instance, you can go for this one. And you see there are two kinds of texts. There's the name of the part and the name of the pads. But for now, it's going to be faster if I just show the traces. Okay. Now let's add another part. It's a regulator, and let's say I'm going to connect it. It's probably going to be nonsense, but I'll put a wire. Okay, so how do wires work? Maybe I will start with a wire that I do myself. So the first parameter is the PCB, then the width of the wire, and after that it's a list of points. Now, points can be referenced by component because if I take my first component here, I see 1, it corresponds to the ATtiny. I can take any pad I want. Pad 0 is the center of the component itself, but after that you start at 1. And then it's the same ordering as in the data sheet. So it top left, and then you turn that way, and that would be basically it for the first point. And let's say the second point is going to be sot.pads2. Yes, I save it, and oops, I also uncommented this one. That's cheating. So there you go. You have a wire between those two pads. Of course, you could add as many points as you wanted. You can also have manual points. For these ones, you specify the x coordinates. Here it's going to be relative to the edge. Let's try that. Plus 0.6. Oops. Didn't like that because there's missing. Yeah. Okay, and now you see the wire has another connection. It's not a connection, actually. It's just an intermediary point. Yeah, so you can see it does this because I told it to first go to that intermediary location. Okay. Now the other thing I wanted to show you is chamfer, because that's a new feature and I think it has potential. So the idea is that you would have a series of points connecting two components. And I have to remove this because those are just points. Okay, so that's our wire, right? And now we want some chamfers. Well, you can simply change the class to chamfer. And by default, you get the tiny chamfer. If you want a larger one...
You're wrapping up.
Sorry?
That was Fran unmuted. Go ahead.
All right. If you want to change chamfer size, you see that you have an additional argument that's called dist, and just like that, you can have a chamfer. Okay. Now, it might seem a bit annoying to design a PCB this way, but you have to remember that if you do it right, then all the positions are relative. So if you move a component, then the wires will move along. Let's try that. I have my voltage regulator and I'm going to move it a bit. And you see that the wire, now it goes down. I can also move the IC. Yeah, okay, that's not a very good location, but the wire will always follow along. That's super convenient. I have only 5 more minutes. Let's show VS and then call it a day. So I have 2 wires, let's say. The second wire, it's on the top of the PCB because all those points don't have a defined Z, so by default it's 0. 0 is the top. You can see here. The top of the board is 0. You could change that, of course, but by default, I think it's good practice because all of those primitives are at 0 by default anyway. So now, if you want it to go through the PCB, you have to add a via. A via is also a component, so you have to add it this way. It doesn't work like a wire. And now I have the pad of the via. If I also want to see the hole, I think I can enable a mode for that. Yes. So in blue, it's the hole in the PCB. Yes. Now, once you've done the via, the smart thing to do would be continued with a wire under the board, and that's okay because all you need to do is change the Z of the points along the wire. So now I'm going to start from the via, the second pad, which is the one underneath the board. The first one is on top, but the second one is underneath. And the second point is going to be, yeah, you see that the wire is now under the PCB. I could also put it on top, simply changing the Z value, and then it changes color to tell you that. But yeah, I think that's all I wanted to show you. Yeah, I have a very brief video about more advanced PCBs. So this is the example from Nicholas. It's a board with an AMD. Nicholas, what is AMD, was it? 11D, yeah?
Correct, yes, 11D.
And this one was to show you the performance. So you see, you have a verbose mode that you can enable. And you see that what takes the most time here is to execute the Python script with these 8,000 lines. And after that, it's pretty fast. It compiles the shader in 18 milliseconds, and the rendering is 5 milliseconds. Okay, so that's one example. And after that, if you want to produce your board, then all you need to do is select only the traces and do a render. That's 1000 dpi, for instance. So in that case, I'm not using frep as a viewer, but to produce the PNG. It still shows it briefly, but after that you get your traces. All right. Yeah, I think. Thank you.
Beautiful work. So yeah, just the two comments. One is, it may seem strange to design this way. A couple reasons I like it so much. One is, instead of lots of clicking and dragging through which menu button does what thing, I can define relationships. So I notion like this part goes relative to that part, and then this trace goes through that pattern over there. I can define a series of hierarchical relationships. And then when you start editing, if you move parts around or change parts, you have all these trees of relationships through the design. That's very different from the way you usually do it with a GUI. Is why I like designing this way so much. And then the reason I choose to put every part I ever used into every file is it's still only a few kilobytes. It's still tiny compared to most just file save formats. But then it frees you from like what you're describing with KiCad, or Chris was describing, of which version has which library. And so each project is standalone without dependencies, and it's just a modest overhead is why I choose to do that.
Yeah, but a community project could be to have JSON files for each of these, so that you could import them as you want, because that would reduce the runtime of that script.
Absolutely, and all of this was aimed at an audience of one, which was me as the user. And so as this migrates into a community project, I think that would be a great thing. By far the most expensive rendering is the text. I made a decision to keep the text in band as an frep, so that which is really powerful, but it's expensive, which is why this is so good.
But I agree with that. I think it's okay.
Yeah. Okay. Really beautiful. Really lovely. So, I think pretty quickly we can migrate to that as a community project.
Yeah, if we have volunteers, then I would like to go to WebGL and write a JavaScript rasterizer, because there's no reason to keep it Python. It's a bit cumbersome.
That was in my queue. I have so many things to do, I probably won't get to it. I would love to see you and whoever else do that.
Yeah. All right.
Okay. Great work.